Good morning, ladies and gentlemen. May I have your attention, please? Thank you. At this time, raise your hand if you did not get red mark for today, the 3rd of February. Great, and thanks for having your reading questions out on your desk so that I can check those. I appreciate it. So we need to be able to solve quadratic equations regardless of, right, how that original equation looks. Depending upon the presence of a linear term mixed in with my quadratic term, I'm going to select and use a different method. So our worksheet number 1, we had to choose the appropriate method based on what the problem looks like. So let's go ahead and do that for our Bellwork today. If I don't have a linear term present in my quadratic, that is no x term, just a single x squared term, then that's the quickest, easiest way to solve. I can take square roots to solve. So I don't have to go through and complete the square and take half of the linear term or any business like that from last time. I can simply add or subtract, multiply or divide to isolate the squaring term, and then undo squaring by taking square roots. So that's the most efficient way if I just have an x squared term. Let's go ahead and do that first one then. I would add 6 to both sides, bless you. Isolate the quadratic term, that's fancy for the squaring term. Bless you. And then I'll undo my squaring by square rooting. So this is just a two-stepper. I'm going to add 6 to both sides, and then undo squaring by square rooting. X squared equals 13. The next is given by the positive and negative square root of 13. Sometimes it will reduce, sometimes it won't. You could box this and still get full credit. I'm still going to break it up into two things just to drive home the fact that, yes, indeed, this is two separate answers, two separate solution values, right? X equals positive root 13, and x equals negative root 13. Raise your hand if you had both of those, please, for number 1. You had both of those? Yes, good job with your multiple solutions. So I know some students struggled back in first semester on having the correct number of solutions for our quadratic equations. We always want to be on the lookout for 2. Doc?
You said that you can use just the normal solving method if one is true. Like
You may solve by taking square roots if what is true?
Like I'm asking.
Yeah. If there's just an x squared term.
Just
Or an x term that's quantity squared. If there's x only appears once in your quadratic equation, then it's a candidate for solving by taking square roots. And so if x only appears once in your quadratic equation, then it's a candidate for solving by taking square roots. If x squared and a separate x term, right, appear, then it's not ready to solve by taking square roots directly. Then I'd have to do another technique like factoring or completing the square. Let's see how that arrives. So take a look at number 2. What's different about number 2 than number 1? Exactly what Jock and I am talking about. There's an x squared term and an x term. There's multiple variable terms in this quadratic equation. So can I solve this by taking square roots? No, not directly. Right? If I tried to take a square root to undo the squaring, I'd still have that 4x hiding inside of a radical. I haven't isolated x. I haven't solved for x. I haven't gotten a single x alone on one side, x equals for a solution. So because there's multiple variable terms in this quadratic equation, I can't solve by taking square roots directly. So I'll go ahead and add or subtract everything on one side set equal to 0 and try to factor. If I have everything on one side and set equal to 0, then I'm going to try and factor it. That's the easiest way to solve if I've got an x squared and an x term mixed together. So I'll go ahead and consider my factors of the last. Right? My factors of the last, negative 5, include plus and minus 1 and 5, and, well, that's it. Could I combine these factors of negative 5 such that they multiply to give me negative 5, but sum to give me this middle term, that is positive 4x? Well, certainly. I make opposite signs because my last term is negative, and I make the larger one positive. And so this is factorable. I'm going to solve it by factoring. How come? Because there was x squared and x in the same problem, but I recognize the factors. We recognize them. We know that if we put those in my lasts, I'll create the factors that multiply to negative 5 and sum to give me a plus 4. Are we supposed to state the method? No, we don't have to. Okay. So I'll go ahead and fill in my variables. The only choice for my first are x and x. That multiplies to give me x squared. My choices for the last are just 1 and 5. And I need opposite signs because my last term was negative, and it looks like I need the larger one to be positive, so I'll put the plus with the 5. And the smaller one negative, I'll put the negative with the 1. Now my outer product, plus 5x, when combined with my inner product, minus 1x, sums to give me the positive 4x. Everybody see it? Awesome. So I'm not done though. I've just factored completely. Now that I have fully factored form set equal to 0, I can utilize the Zero product property. I know the only way for these things to be multiplied together and have a result of 0 is if the first thing equals 0 or the second thing equals 0. So I'll go ahead and break this up into two separate equations. I'll set each factor equal to 0 and solve separately. So x minus 1 could equal 0 or x plus 5 could equal 0. Now let's go ahead about my business using our regular inverse operations. So for the first equation, it looks like I'll add 1 to both sides. We'll get the potential solution value x equals positive 1. On the right-hand side equation, I'll simply subtract 5 from both sides and get the potential solution value x equals negative 5. And before I box it, I'm going to make sure I check. So let's go back into the original. If x is 1, 1 squared is 1, plus 4 is 5, is 5 minus 5 equal question mark 0? Yes, so this one's an answer. Yeah. And negative 5 in the original, negative 5 quantity squared is positive 25. Plus 4 times negative 5 is minus 20. 25 minus 20 is 5 minus 5 is 0. So this works as well. Cool. So we found both solutions. Raise your hand if you had 1 and negative 5 for number 2. You get 1 and negative 5? Way to go, you guys. Now, you could have solved this via completing the square. However, in my opinion, solving by factoring is quicker, right? Less steps. I didn't have to do any of the half of the middle number and then squaring it and then adding to both sides. And so we certainly are going to have to solve by completing the square, but I always check to see if I can factor it first, if there's an x squared and an x term. Remember, if there wasn't an x term and only the x squared term, I wouldn't be trying to factor at all. I'd be solving by taking square roots. That's the most efficient method if I only have a squaring term. Let's try another. Can I solve this one by taking square roots? Right? Can I solve this one by taking square roots directly? Taylor? No, how come? Absolutely. I've got the x squared and a 3x term. I've got multiple variable terms in the same problem. I can't solve it by taking square roots directly. So I'll try to solve it by factoring. So my best first step for factoring is to get everything on one side and set equal to 0 and try to factor. So my best first step here, if I'm going to try to solve by factoring, is to subtract the 12 over. Now, you didn't have to do it this way, but in my opinion, it's more efficient if I can factor it than it is to solve by completing the square. So I'm going to try factoring first. If I can't factor it, then I'm going to scooch that 12 right back over, and I'm going to subtract the 2 over, and I'm now going to complete the square. But first, let's try factoring. So let's see if factoring works. Rewrite in standard form, x squared plus 3x minus 10 equals 0. I've got the standard form, everything on one side set equals 0. Let's try to factor. Let's try to factor. So I'll consider my factors of the last, negative 10, right? Then multiply to give me negative 10, but sum to give me the middle term. So let's see if that's possible. I'll try 1 and 10, or 2 and 5, or 3n, 4n, nothing. So I've got all my choices for 10, right? Do one of these integer pairs, right? Do one of these integer pair of factors multiply to give me a negative 10, but sum to give me a positive 3? Most certainly. And so this is factorable. I'm going to solve by factoring, right? And I'm glad that I tried to solve by factoring first, because this works out nicely. So go ahead and tell me the placement now of my factors, whether you did it this way or not. Go ahead and tell me what I put in those parentheses to make my outer and inner product sum to give me that positive 3. What would I have to put in those parentheses to make this work out? Go ahead and share with the class when I call on you. Go.
X plus 5, x minus 2.
X plus 5 and x minus 2. Raise your hand if you agree with Kendall. X plus 5 and x minus 2. Good job. My outer product, negative 2x, when combined with my inner product, plus 5x, sums to give me the middle term, plus 3x. Nice job. Now, that's not the answer. That's fully factored form. Set equal to 0, I can now utilize the 0 product property. I'm going to set each of these individual factors equal to 0 and solve separately. So in the first equation, x plus 5 equals 0. Or in the second equation, x minus 2 equals 0. Then I would guarantee that the product of those two quantities had to equal 0. Now I'll solve separately. It's easy cheesy. In this case, I subtract 5 from both sides. So my first potential solution value is x equals negative 5. On the right-hand side equation, I'll add 2 to both sides. So my second potential solution value is x equals 2. A quick check in the original, negative 5. Quantity squared is positive 25. Minus 15 is 10. 10 plus 2 is 12. The second one, 2. 2 squared is 4, plus 6 is 10, plus 2 is 12. I feel like we're winning today. We're winning. Winning. I like it. Winning. Don't want to lose. Want to win. Let's win. Raise your hand if you won too. -5 and +2. Great job, you guys. So we've got factoring, right? Factoring is an efficient strategy, right, to use for solving when we have an x squared and an x mixed together. So let's try it again. I've got both x's and x squareds. I'm going to try to solve by factoring. So I'm going to subtract over that 2x and set it equal to 0 and try to factor. So if in the course of, right, in the course of trying to solve for factoring, I consider the factors of the last, then multiply to give me -2, but sum to give me -2. Is this factorable? No, no combination of 1 and 2 opposite signs will sum to give me -2. I could get -1, I could get +1x, but I'm never going to get -2x with an outer product and inner product that come from these integer pairs. So guess what? I can't solve this one by factoring. This is not factorable over the integers, so I can't factor this. If I can't factor this, that's when I'm going to use completing the square. And that's when, right, completing the square is the most efficient method. If I can't factor, I've got x squareds and x's in the same problem. If I can't factor, then I'm going to solve by completing the square. So what do I do for completing the square? That's when I add over the number or subtract over the number and get the x's along on one side, right? So I'm going to go ahead and add this 2 over and set up for completing the square. What do I mean set up for completing the square? I mean write my x's along on one side, scooch the equal sign over, leave space, because I'm going to complete them. I'm going to find that special number that I add to both sides to make a perfect square triangle. So I'm going to go ahead and say my second favorite game, that is complete the square, right? So I'm going to take half of my linear term magnitude and then square it. That's a special number I'm going to add to both sides, like the pattern we set up last time. So everybody, you can help me out in your head. I'm going to take half of the middle number. Half of the middle number, -2, is -1. I'm going to square that. -1 squared is +1, and add that number to both sides. So it looks like +1 is my special number that I'll add to both sides to complete the square. The whole point of doing that is so that I can take this equation that has x squareds and x's in the same problem and rewrite it as a single variable term, quantity squared. Yes, that's right. My x squared minus 2x plus 1 can be rewritten as a binomial squared. In fact, we already know what the entry is because we already did half of that linear term. What's half of -2? -1. I already know my entry is x minus 1. We already did that -1, then we did half of that x term. Equals, meanwhile, back at the hacienda, all I do is combine like terms. 2 plus 1 is 3. So I've gone ahead and rewritten my equation that x squared and x is in the same problem as a single x term quantity squared. You guys see it? Now I can solve by taking square roots. That was the whole point of completing the square. Now I can solve by taking square roots because now I just have a single x term quantity squared. All right, let's undo the squaring then. When I'm done squaring, square rooting, if x minus 1 quantity squared equals 3, then x minus 1 is equal to the positive and negative square root of 3. Sometimes that square root will reduce, sometimes it won't, but either way I'll be able to break it up into my 2 separate paths. In the first path, x minus 1 is given by the positive square root of 3, or root 3. In the second path, x minus 1 is given by the opposite of square root of 3, that's negative root 3. And now I can finish out by adding 1 to both sides. I'm going to go ahead and put my rational number, that number 1 first before the radical, so I'm not confused as to what's inside versus what's outside the radical. And the book will do that for the answers too. So I'm going to go ahead and add over the 1 and get positive 1 plus root 3. I'm going to add over the 1 and get positive 1 minus root 3. There's my 2 separate solutions. That's pretty cool. This was an important Bellwork because it summarizes not only the different strategies we use to solve quadratic equations, but when do I pick which method? When do I choose which method? If there's just an x squared term and no x term, I'll solve by taking square roots. If there's both an x squared and an x term mixed together, I'll try to factor. If there's an x squared and an x term mixed together and I can't factor, then I'll use completing the square. So that's kind of my flow chart that I use mentally in my head. What kinds of questions do you guys have about today's Bellwork? Awesome. Then let's go ahead and solidify what we just discussed. When is it most efficient to solve by taking a square root? So when is it most efficient to solve by taking a square root, that is without having to complete the square? Versus when is it most efficient to solve by factoring? Versus when is it most efficient to solve by completing the square? All right, so let's go ahead and summarize that. You can go ahead and write down in your own words. We just talked about it. We had this right before I closed your last class. So when's the most efficient by solving by taking square roots? You can write in your own words. You don't have to put exactly what I put. So one way we could provide a reason for solving by taking square roots is that there's just a single squaring term, whether it's parentheses squared or x squared. There's just a single x squared term and no linear term, no x term. There's not multiple x's in the same problem. Versus in the same quadratic equation. Versus when is the more efficient to solve by factoring? Both x squared and x terms mixed in the same problem. So I've got multiple variable terms, multiple x's in the same problem, an x squared and an x, but I could factor it. So that's what I want to solve by factoring. So both squaring and linear terms present in the problem. I can factor, and I can factor. So if there's both an x squared and an x in the same problem, then I'm going to try and solve by factoring. Remember, that's when I subtract, add or subtract to get everything in one side standard form, set equal to 0. So that I can factor completely and utilize the zero product property. Set each factor equal to 0 and solve separately like we did for number 2, and number 3, and number Bellwork. Lastly, number 3, same thing. I've got squaring and linear terms, but I can't factor. Either it's unfactorable, or I'm not good at factoring, or I don't recognize the factors. Then I'll use completing the square as kind of my last resort. So same kind of reason. Both squaring. Uh-oh. I don't know what's going on with that little took right there. So both squaring and linear terms are present. But I can't factor. Little gadget arm. So if there's both an x squared and an x term floating around in the same equation, I put it in standard form set equal to 0, but I can't factor it, then I'm going to go ahead and solve by completing the square. Then I've got to do the half the middle term, right? Square it, add that special number to both sides, etc., etc. What questions do you guys have about our strategies? Awesome. So we got big things on the horizon. I just want to make sure that, as you know from your purple sheet, right, we've got a quiz coming up on day 5, and today is day 4. So we want to make sure that you're setting aside some time to practice and prepare for your quiz. We put together an informational slide that will share the content and objectives on your quiz, and it does include today's discussion where we model projectile motion. That is, we use our graphing calculator technology and quadratic equations to do something, right? To do something in real life. And so this is a great real life application of quadratic equations. But first, let's go ahead and give yourself credit for your homework assignment. We're going to start the stapler, and I'm going to pause the recording. Let's go ahead and remind yourselves about the different options that we have for next year's course registration, and we're just going to do it briefly today because we spoke at some detail last class period. Remember, the vast majority of you, right, who are thinking about going to 4-year college, on-track course for next year would be FST, whether you're a sophomore or a junior next year. If you're doing well in advanced algebra, you could take FST and possibly with a resource if you wanted some increased access to a math teacher and support to make sure that you do well again next year. Some of you are juniors, right? Currently, that might be interested in attending an area technical school, right? You can earn dual credit if you take senior algebra next year, so that's something to consider. You could always retake advanced algebra if you're not doing well this year, and that's true whether you're a sophomore or a junior, but you want to make sure you have the advanced algebra for a 4-year college admissions requirement. Then you could go ahead and retake advanced algebra to make sure your skills are sharp, and then possibly include the workshop course that goes along with it or the resource course offering to go along with it to make sure that you have that needed support so you can do well. If you're a high-achieving sophomore or a very high-achieving freshman, you could apply to take the compacted course. If you do that, please note you'd be missing out on some essential statistics material from the FST course that would have to be remediated some other way. You could do that, right, by taking a course over the summer. You could do that by taking AP Stats, would include all that missed stuff, and you'd have plenty of time to do that if you're currently a sophomore or a freshman. And so there's options to make sure that you still get your statistics. But if you want to make sure that you get AP Calculus while you're still in high school and you're a current sophomore, the only way to get there is to take the compacted course. That's not just gained by signing up, you've got to apply for it, and we'll talk about all the details of that during informational sessions next week. If you'd like to apply for the compacted course, come to one of the contact times and pick that on your FlexiSched offering, starting at Friday, 3:30 afternoon when it's opened up to students. Go into FlexiSched and pick me for Tuesday. Mr. Aker, Mr. Marks, or Mr. Notsky are each having one of the days, Tuesday through Friday, for an informational meeting regarding the compacted course application. You have to come to that, and you'll get your application paper then. Lastly, if you're a small segment of the population that knows exactly what you're doing and it has absolutely nothing to do with math and you're currently a junior, then maybe you could not take math next year. I don't recommend it, of course, because I'd like you to keep your skills sharp, right? And you probably want to keep your skills sharp if you're going to have to take math, but there are a few of you that might not take any math with their college majors. All right, let's go ahead and direct our attention to today's content objective. We're going to use quadratic equations to do stuff, to model real-world situations. And so anytime we're working with projectile motion, we can utilize quadratic equations as a means for modeling that motion. And that I'm super excited about today because we're going to use math to, well, do stuff, right? Problems involving distance, velocity, acceleration, motion. We're also going to graph and interpret quadratic functions, and that's why we need our grapher today. So thank you for signing out and including your calculator number when you signed out. Lastly, a quiz next class, and we did put together an informational slide. We'll share that at the end after closure so you can see exactly what will be on the quiz. All right, so a common application of quadratic functions could include the path of a punted soccer ball. So let's suppose that you punt a soccer ball and sketch, right? Sketch the graph of that, the path of that punted soccer ball. What would it look like in general? Well, if I were to punt a soccer ball, we've all done it, right? And it would look like a parabola, where the ball goes up for a time, slowing down until it reaches its apex, right, the top of its path, and then it would start coming back towards Earth slowly at first, and then picking up speed until it ultimately hits the ground again. So in general, the path of a punted soccer ball would be, well, a parabola. We're going to use that fact to get quadratic equations into the mix. We're going to use quadratic equations to model the motion of a projectile motion. What's projectile? Anytime we kick something, punt something, throw something, right? As soon as we're done doing the kicking, the throwing, the punting, imparting the force, the loosing of the arrow, then if the only force acting on that object is gravity, we're dealing with a projectile. And so something flying through the air, we're talking about a projectile. All right, so this is a huge informational slide with a bunch of words on it, but all we want to know is that gravity is determining, right, the course of motion for any object that's flying through the air. As soon as you're done kicking it, shooting it, punting it, right, loosing it, anything like that, then gravity is the sole force acting on that object. We're going to go ahead and generate the equation for a general projectile based on the acceleration due to gravity and initial velocity that's imparted upon that object. And so we're going to skip over that slide and get right to our general form for the quadratic equation. The general formula developed for the height h of an object at time t seconds with initial velocity v naught or v sub 0 and initial height h naught or h sub 0 is given by h equals negative 1/2 gt squared plus v sub 0 times t plus h sub 0, where h is the height of that object, right, at any time t. So h is the height of the object at any time. T is the time in seconds since the problem began. G is the acceleration due to gravity. And that constant g is different depending upon if we're working in feet versus working in meters. If we're working in feet for our measurement of distance, then g is given by 32 feet per second squared. If we're working in meters, then g is given by 9.8 meters per second squared. In my equation, this will always determine the coefficient on my quadratic term on the t squared. If we're working with feet, then that negative 1/2 g will always be negative 16. And so if we're working with feet, then we'll always have a negative 16 for my quadratic equation, coefficient on the t squared. If we're working with meters, then my squiggle underline negative 1/2 times g is always going to equal negative 4.9. If you see a negative 4.9 on your t squared term, on your quadratic term, then I know I'm going to be working in meters. Uh-oh, uh-oh, uh-oh. I can totally fit it. Lastly, v sub 0, right, or v naught for short, is referring to the velocity at time t equals 0. The velocity when the problem starts, we'll call that the initial vertical velocity. And this is only vertical velocity. So we're just talking about what vertical component of your velocity. Even though when we kick a soccer ball, we could kick it, right, both forward and up at the same time, this v sub 0 refers to the vertical velocity, the straight up speed. So v sub 0 is referred to as the initial vertical velocity. H sub 0 refers to the initial height above ground at time t equals 0, if any. And so h is the height of the object at any time t since the problem started. T is the time in seconds. Regardless of whether we're working with feet or meters, time is always measured in seconds for this equation. G is different depending upon whether we're working with feet or not, and all that does is influence my coefficient on the squaring term. If it's negative 16t squared, blah, 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 I know we're working in feet. If it's negative 4.9t squared, blah, 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 I know we're working in meters. That's a free-for-all. It's a giveaway. And then lastly, v naught refers to the initial vertical velocity. When time t equals 0, when the problem starts, what's the initial vertical velocity of your object? And h sub 0 is the initial height above ground. When the problem starts, how high is the object above ground? Let's go ahead and do some together then. Suppose a thrown ball has height h equals negative 16t squared plus 42t plus 7 after t seconds. We can go ahead and find h, the height of that object above ground, when t equals 0, 1, 2, 3, and 4. Explain what those order pairs mean. Graph it over a given domain. And then go ahead and answer a variety of different application questions. So I'm going to go ahead and scooch so I have a little bit more room. All right, everybody, to the graphers. Let's enter our original function into our graphing calculator so that we can answer some questions here. All right, so on our graphing calculator, we're going to go ahead and go into our y equals menu. Make sure your plots are off. Make sure your plots are off. Remember, we can do that by up arrowing and highlighting the given plot and pressing enter to toggle it off. You want to unhighlight it. So all your plots should be unhighlighted. Then we'll enter our negative 16t squared. I'll use the variable button for x. The variable button's up here. Plus 42t plus 7. I already know some key things about this function. I already know that because my x squared term has a coefficient of negative 16, I already know what system of measurement I'm working with it. Are we going to measure our height in feet or in meters? I already know we're measuring my height above ground in feet because my leading coefficient was negative 16. So we must be working with feet. I already know my initial vertical velocity. That's the multiplier on the linear term. My v sub 0 is 42. So I already know that my initial vertical velocity is 42 feet per second. I already know my initial height above ground. That h naught at the end of my equation is 7. So it must be starting out at a height of 7 feet above ground. All right, let's go ahead and find h when t equals 0, 1, 2, 3, and 4. So the easiest way to do this is to go ahead and go to your table. If I'm going to be evaluating h for multiple time values, the easiest way is to go to your table. We could ask or we could scroll. Either way, we're going to do second graph. Second graph is going to give you your table. I can look at what h values are produced when t equals 0, 1, 2, 3, 4, etc. So second graph does table. Everybody do that? Second graph brings you to your table. Everybody find it? Great. So we can see the values of h, right? The values of h when t equals 0, 1, 2, 3, and 4 are represented by my y sub 1 column entries in my table. When t equals 0, my height above ground is 7 feet. Right, 7 feet. When t equals 1, my height above ground is 33 feet. When t equals 2, my height above ground is 27 feet, and so on and so forth. What do those pairs tell me? They tell me after 0 seconds have passed, I'm 7 feet above ground, and so on and so forth. So let's graph those over my interval shown on the domain. Here we go, everybody. 0, 7, about here. 1, 33, about here. 1, 2, 27, about here. 3, negative 11, what? That's about here. 4, negative 81, what? That's about here. As I graph those ordered pairs, right? As I graph those ordered pairs, can you see a parabola, right? A curved function here? Absolutely. It's just an upside down parabola. Well, that makes sense because we already punted, right, our soccer ball and recognized that path as an upside down parabola. So it makes sense that this is going to look like a parabola as well. Okay, so I've got my graph with those ordered pairs. And now let's consider, is the ball moving at the same average rate between 0 and 1 as between 1 and 2? Well, that's an interesting question. So from t equals 0 to 1 seconds, is the ball moving at the same average rate? Remember, rate would be a change in y units over a change in x units, as between t equals 1 and 2. What? Well, from 0 to 1, it looks like I went up. 7 to 33 is up 26, right? Up 26 feet in 1 second. Versus from 1 to 2, I went from 33 to 27 feet above ground. That's down 6 feet in 1 second. Is that moving at the same average rate? No. Can I have a negative rate? What's going on with the ball between 1 and 2? What's going on with the ball between 1 and 2? Mark?
Falling.
It's falling, so I'm going to have a negative rated change in its height with respect to time. Absolutely, good. Let's go ahead and take a look at some other questions. What was the speed of the ball when it left my hand? I can answer that without doing any calculations. In fact, all I need to do is identify the initial vertical velocity. That's the coefficient on the linear term. And so it turns out that I can determine the speed of the ball, the vertical speed of the ball when I left my hand, simply by looking at my equation. However, because this is a speed, my units I must report, they're not going to be feet, right? What would speed be measured in the context of this problem? How do I measure that speed? Would that be in seconds? No. Would it be in meters? No. What would it be in? Feet per second. Right? Feet per second. And we're going to have to include those units for speed, right? Either meters per second or feet per second on our quiz. I think I better add that on our last one. I didn't add. Our average rate of change was 26 feet per second versus -6 feet per second. And Mark said, what was happening here? The ball was falling down. That constituted the negative in my rate of change. Now I feel better. Now this is PDFable. F. What was the height of the ball when it left my hand? Guess what? Another problem I don't need to do any calculations for. I can simply look at my original equation and find h sub 0. Right? H sub 0. H sub 0, unlike v sub 0, is the constant term in green. It's the initial height of the object above ground when the problem starts at t equals 0. That's where that little subscript comes from. What's that? 7. What's the label? Feet. So we get the initial height above ground at time t equals 0 for free as well, if I have the equation. What is the vertical speed of the ball at its maximum height? Well, this is a great question. Again, I don't have to do any calculations. Instead, I can do this about thinking about the path of the ball. So as the ball travels through the air, it goes up for a time, and then it goes down for a time, and then it hits the ground. What's the vertical speed of the ball at its maximum height? Well, where is its maximum height? That's right here at the apex of the ball's path. On its way up, its vertical speed is positive, right? Its vertical speed is positive. On its way down, its velocity would be negative. And so what must its vertical speed be at the maximum height? 0. It's neither going up nor going down. Therefore, the velocity is neither positive nor negative. So at the split instant, when the ball is at its maximum height, its speed is 0. It's when it's stopped. It's suspended for that instant, where it's neither traveling up nor traveling down. Its vertical speed would be 0. That's pretty cool. And again, units on speed, feet per second in this problem, because it was a -16. That's my leading coefficient. So I know we're working with feet. Therefore, speed's in feet per second. H, what's the maximum height for the ball? In order to do this, we'll use our graphing calculator. So to find the maximum height, we're going to go ahead and figure out the height h. That's the y-coordinate of my function when it's at its maximum. So what can we do? Well, we're going to go ahead and graphically determine that. So what was our window given? It went -1 till 5, and it went -100 to 60. If I wanted to make that same window, right, I'd get that same picture. It looks to me like we don't need all that negative business, but I'll make it look similar. So let's do -1 for x min. Everybody, remember, window is your top toolbar second button. Let's manually set our window. Let's go window, -1 to 5. Leave your x scale as 1, please. And let's make our y min. We don't need all the negatives, but we'll make it match. So I feel good about our export as a PDF. Y max was 60. All right, let's go ahead and see what kind of picture this produces. If we wanted to calculate the maximum height of that ball, of that projectile, I could use the calculate menu and calculate maximum. And so to do that, we're going to use a similar process from our calculating 0 2 class periods ago. Ready? This is very important. Everybody follow along. Second trace is the calculate menu. So we're going to second trace, that's the calculate menu. And we're going to pick not 0, we're going to pick maximum. So the fourth option. So we're going to pick the fourth option here. So we're going to do second trace is calculate, and we're going to do the fourth option. That, not upset. I'm just disappointed. Or the fourth option, maximum. Fourth option, not the fifth option. Fourth option. And now the calculator is going to ask us for left bound. This means you have to use the arrow keys to go with the cursor to the left of where you think the feature occurs. And so depending upon what window you have, you may already be on the left or the right, right? You just want to make sure that before you press enter to answer the prompt left bound, you are to the left of your feature. We're looking for the maximum, so use your arrow keys to go to the left of where you think it occurs. Enter. The calculator asks for a right bound. Please use your cursor to go to the right of where you think the feature occurs. I'm going to go past it so I'm safe before pressing enter a second time. And lastly, it asks for a guess. So you're now going to go ahead and use your arrow keys to go close to where you think the feature occurs before pressing enter a third and final time. And voila, when your calculator says maximum, you know you're done. Just like when your calculator said 0, you knew you were done. If it doesn't say maximum, then you haven't completed all 3 steps. So everybody make sure you can do it. Second, calculate, maximum, left bound, enter, right bound, enter, guess, enter, and then it should say maximum on your screen. This is telling me 2 separate things. It's telling me the x comma y coordinate of my maximum point. The point on the graph is 1.312 ... 34.5625. Which one is the height value? 1.312 or 34.565? Well, what did I put in my y equals menu? Hans?
34.
Yeah, absolutely. I put in my height for y sub 1. I put in h equals for y equals. So y, the y coordinate must be my height. So yes, it's the 34.5625. Make sure we include a label. So 34.5625, and I'll label that as feet. And then I'll answer when the ball is at its maximum height. That's the x coordinate. That's the time value. And so that is the 1.312. And we'll call that seconds. Awesome work, you guys. What questions do you guys have about this first one? That's pretty sweet. Mr. Marks throws the ball into the air such that its height h above ground after t seconds is given by h equals -4.9 t squared plus 25.2 t plus 2. We can answer all kinds of questions, like, is h measured in feet, meters, or yards? Well, to determine that, all you need to do is look at my coefficient on the squaring term, my t squared term. Everybody find it. Since my coefficient on the squaring term is -4.9, I know that I'm working with which measurement system? I must be in meters. And so we get that information for free just by looking at my equation. We must be working in meters because of the -4.9 t squared term. The initial vertical velocity, v naught, we also get for free. Because of its placement in the equation, I know that's the coefficient for my linear term, my t term. So guess what? We don't have to do any calculations for that. My initial vertical velocity v sub 0 is 25.2, but I do need the correct label. So think about what label for velocity would be. That would be distance over time, in this case meters per second. From what height does Mr. Marks release the ball? So I'll go ahead and look at my original problem. Remember, my problem starts as soon as it's done being kicked, thrown, punted, loosed, right? As soon as that initial force imparted upon the object, rather, is done, then the problem starts. So it looks to me like the height that Mr. Marks releases the ball is at 2 feet above ground. Nope, 2 meters. Good job. I'm like 2 feet above ground, that's kind of low. Oh, it's because we're working with meters, aren't we? 2 meters, that's a little bit more reasonable. How high is the ball after 2 seconds? Well, for this, we do have to do a calculation. It's as easy as evaluating my function rule that gives the height h after t seconds for a time t value of 2 seconds. So I'll simply evaluate my function rule when t equals 2. So I could do this directly and evaluate my function rule. Except everywhere I see a t, I'm not going to put t, I'm going to put 2. I can evaluate this on my home screen. Everybody, we'll go to my home screen, second quit. Clear out, and on your home screen you can simply evaluate negative 4.9 parentheses 2 close parentheses squared plus 25.2 parentheses 2 parentheses plus 2. I'm simply evaluating my function rule. Everywhere I see a t, I'm putting 2. You could do that on your home screen. I'd get 32.8 meters. I could also enter this into my function, my function menu, y equals, and then go to my table when t equals 2. Didn't we do that already with a different one? So clear out the old business. Zoom 6 to be a good calculator neighbor and return your window to its standard setting, zoom 6. And in my y equals menu, put our new function. Our new function was negative 4.9 t squared. Everybody do it, please. Negative 4.9 t squared plus 25.2 t plus 2. Remember, you're using the variable button t, right here, but it's spitting out an x every time, but you're using this variable button right here, second row, second column. After I get my function entered, right, I could go to my table, second graph, and see what y value is returned when x equals 2, and by golly, I get the 32.8. Everybody get it? So you can do it in your table too. Finally, we can do it graphically. If I adjust my window, I can determine, right, a good window by considering the problem. So it looks like my original function, y equals negative 4.9 t squared plus 25.2 plus 2, right? I'm going to go ahead and say, if Mr. Marks threw a ball into the air, I'm thinking a good window to start at, right, might be 0 to 6. And if I need to adjust it, 0 to 6 seconds, I certainly can. So I'm going to go a little bit past negative 1 to 6. And for my y window, I know that I can't go beneath ground, but I want to make sure I get a good picture. So I'm going to go ahead and go down 15, and I'm going to go up 60. Now, I don't know if this is a good window or not. I chose negative 15 as my y min and 60 as my y max, and this may not be a good window at all. But I don't know unless I check. I can always go back and manually adjust it. Am I able to see the path of the ball? Yeah, I think that's an okay window. So I'm going to go ahead and keep that as my window. So I went ahead and did All right, let's go ahead and answer some more questions then. When does the ball reach its maximum height? Well, first I want to do one more thing with our trace. So what do we say? After 2 seconds, we're at 32.8. Final way to do that would be to do trace. Everybody look, top toolbar, fourth button, trace. Enter the x value concerned. We were concerned when x equals 2. Enter, and the cursor will jump on the graph at the x value 2 and pair with, surprise, surprise, 32.8 meters, right? So you can always trace the function value too. All right, now let's go ahead and do our last one. So when does the ball reach its maximum height? That's the time value when that maximum has occurred. So what do? That's my calculate menu, you guys. That's my second calculate maximum. So I'll go ahead and do second. Oh, I can do that. Great. So that's my second. Trace is the calculate menu, maximum. Left bound means go to the left. Everybody do it. Go to the left of where you think it occurs. Enter. Right bound means go to the right of where you think it occurs. Everybody do it. You're going to show your partner that you get the word maximum. Enter. Go back to get a guess. Enter. And when your calculator says maximum, go ahead and show your partner that your calculator says maximum. If it doesn't say it, then help them get it. So everybody needs to be able to get second calculator. Maximum. Left down, right on there. So take maximum on your calculator. Show me you can get it. What? So 2 different answers here, guys. The coordinates are 2.571 ... 34.4. When does the ball reach its maximum? That's an x value, a time value, an independent variable value. So that must occur at the 2.571 seconds. Versus what is the maximum height? That's the y coordinate. That's the 34.4, and that's in meters. Finally, with our graphing calculator, we could answer important questions like, how long is the ball in the air? And so what portion of the graph are we concerned with when we ask the question, how long is the ball in the air? Well, that's right up until here. And so we're going to do second calculate 0 to find the x-intercept of this graph. Everybody, one more calculate. Let's do it. So we want second calculate. This time we want 0. All right, this time we want 0. So I'll go ahead and pick the second option. Left bound, I need to press enter when my cursor is on the left side of where I think the intercept occurs, and so I'm just going to press enter right now. Right bound means go to the right of where I think it occurs. So this time I've got to go all the way till I think I'm past. So I think I'm to the right of where that x-intercept occurs. So this time I do have to move the cursor. Oh goodness, getting carpal tunnel. So am I to the right of it? Yes. 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 You know you're not done until your calculator says the feature that you've calculated. In this case it says 0. So I found my x-intercept. It's telling me y equals -1e -11. What's that business? Almost 0. That little e is for exponent, scientific notation times 10 to the -11. That's like 0.00000, 10 zeros and then 1. Very small rocks. So that's trying to tell me 0. It's doing its best. So this is basically 0. So it looks like 5.221 seconds. It's pretty sweet. So I'm getting 5.221 seconds. Awesome. What questions do you have about Mr. Marx's problem? 2 to go. Jacob drops a ball from the roof of his apartment building. The ball's initial height is 12 meters. Find an equation for the height of the ball after t seconds. If Jacob is dropping a ball, right, then he's not kicking it, throwing it, punting it, loosing it, shooting it. It means that the only force acting on it is gravity. There's no V naught. There's no initial vertical velocity if he's dropping something. So my equation, right, the linear term, that V naught times t term, disappears. And my equation is just H equals, right, H equals negative G times 1/2 t squared. If this is meters, it would be negative 4.9 t squared. And then plus my initial height. In this case, plus 12. Ooh. So my original equation is given by negative 4.9 t squared plus 12. What happened to the t term? Because you're dropping it, the initial vertical velocity is 0. So that linear term drops out. We don't need it if you're dropping something. That's going to come in handy on your quiz. So if you're dropping something, the initial vertical velocity is 0. There won't be a linear term in your model. Find the height of the ball after 1/2 second. Round to the nearest tenth of a meter. Okay, we can evaluate my function rule, h, when t equals 1/2. So I'll evaluate my function rule when t equals 1/2 and see what I get. That's as easy on my home screen as doing negative 4.9 1/2 squared plus 12. My height above ground is 10.775 meters, right? So 10.775 meters. Pretty sweet. And lastly, after how many seconds has the ball hit the ground? After how many seconds has the ball hit the ground? Can we do that? Yeah, we can do that. In order to figure out when the ball hits the ground, right, what would be true about the value of h when the ball hits the ground?
0.
Yeah, h is 0 when the ball hits the ground. So I'll rewrite my original equation, h equals, but I'll set it equal to 0 and solve for t. That'll tell me the time t when it hits the ground. So once again, if I want to know at what time t the ball hits the ground, I'll set h equal to 0, right? H equal to 0 and solve. So it looks like I'll subtract 12 from both sides and get negative 4.9 t squared equals negative 12. Divide both sides by negative 4.9 to solve for t squared. And then get t by taking the positive and negative square root. Because time t in seconds must always be positive, this is one of the few times when I won't include the negative square root, right? I don't want the negative time value, I only want the positive time value. And so while I undo squaring by square rooting, I'll only consider the positive square root value because time t is positive. Let's do it. Ready? The square root of inside 12 over 4.9. Close radical. It looks like the ball hits the ground after, no. It only takes 1.564 seconds. No, that's possible, because after one, how high was it after after a half second, it was a half second. I was thinking we already did it for 2 seconds. That was the previous one. So after a half second, it was 10.7. So it's plausible then after another half second, then it's down to 0. So yes, that's certainly plausible. That seemed a little bit too small, but I guess not. So about 1 point, bless you, 565. And what would the label on that be?
Seconds.
Seconds. Good job. All right, ladies and gentlemen, we're 1 to go. In a football game, David punts the ball from a height of 2 feet. The ball stays in the air for 3.2 seconds before hitting the ground. Find the initial upward velocity, that's my vertical velocity, of the kick. What? In a football game, David punts the ball from a height of 2 feet. Okay, so I know that's my initial height, h sub 0. The ball stays in the air for 3.2 seconds before hitting the ground. So that's my time t until it hits the ground. And then find the initial upward velocity of the kick. My initial upward velocity is v sub 0. Let's start with my original equation and see what we can fill in. So my original projectile motion equation is given by h equals, because we're working with feet, I'm going to use the 16 or the 4.9? 16. It's always negative because it's an upside down parabola. So everybody, you get the negative 16 t squared for free because we're working with feet. Plus v naught times t plus h naught, where v naught is my initial vertical velocity and h naught is my initial height. So which of any of these things do we know? We know t. We know the time that it's in the air until the height is 0, it hits the ground, and so we've got h would be 0 when it hits the ground. We know t is 3.2 seconds. And we know my initial height is 2 feet. So we have an equation where I can replace h. My height above ground after t seconds is 0. After 3.2 seconds for t. My height above ground at the start was 2. The only thing I'm missing is one variable. What variable am I missing in this equation? V sub 0. Isn't that what I'm looking for? Awesome. Let's solve for v naught, you guys. Let's solve for v naught. So what am I going to do? I'll go ahead and multiply that, add it with this, subtract over, divide by 3.2, and I'm done. So I'm just going to use my regular home screen on my calculator. I'm going to do negative 16 times 3.2 squared. So I'm getting 0 equals negative 163.84 plus 3.2 times v sub 0 plus 2. Same side, same operation. I'm going to go ahead and combine that with the positive 2 and get negative 161.84 plus 3.2 v naught. When I add over, oh, jeepers. When I add over my 161.84 and finish it out by what? Division? All right, let's do it. 161.84 divided by 3.2. Survey says looks like about 50.575. What in the world? What would my label on that be? Feet per second, and now it's reasonable. So 50.575 feet per second. Awesome. Great work, you guys. What questions do you have about this last one? So by starting with your projectile motion and plugging in those values we know, we can solve for the remaining variable that we don't know. So that's kind of sweet. I'm going to go ahead and undo the auto hide so we get a nice full picture here. All right, let's go ahead and summarize our new learning for the day then. So when working on a projectile motion problem, go ahead and write down on your closure slide, please. Don't talk, just write down what does V sub 0 stand for? What does H sub 0 stand for? How can you tell if you should use G equals 32 or the 9.8? How do you determine how long an object is in the air? How can you quickly find the minimum or maximum of a parabola? And again, we'll assume you're using graphing calculator technology for number 3 and number 4, okay? Awesome. So in my projectile motion equation, V sub 0 stands for the initial vertical velocity. What does H sub 0 stand for? Hannah? Good, the initial height above ground. Thank you. Initial height above ground when the problem starts. How do you tell whether you should use G is 32 or G is 9.8, right? What in the problem will tell you which to use? Blake?
We use 32 if it's in feet and 9.8 if it's in meters.
Awesome. We use G equals 32 if we're in feet, making sure that our quadratic coefficient will be negative 16 versus 9.8. Thank you. You would use it if you're working with meters. Awesome job. How do we determine how long an object is in the air? 2 different ways, right? 2 different ways. One, algebraically, we set H equal to 0 and then solve for T. Or graphically, we graph second trace is the calculate menu, 0, and find the x-intercept graphically. So we could graph it and then find the x-intercept graphically by doing second calculate 0, the second option. And lastly, how can we quickly find the minimum or maximum of a parabola? Again, graphic calculator technology at our disposal. Graphically, then second trace is the calculate menu. And we want maximum or minimum. Great work, you guys. You can go ahead and pack up. Just make sure that you don't get up. If you borrowed a calculator at this time,